Chapter 3, N Recovery. In Step 3, you choose the N Recovery process. Upstream P recovery is needed to implement any choice involving ammonia stripping. Ammonia stripping involves transferring ammonia from the liquid waste stream to air by contact over a large surface area. Ammonia stripping columns typically utilize packed media to foster mass transfer between two countercurrent streams. The process is governed purely by liquid to gas phase diffusive mass transfer and does not involve chemical or biological reactions. Air rich in ammonia is passed through a recovery process, which is basically another packed column where it is contacted with sulfuric acid to produce ammonium sulfate fertilizer. For effective N recovery, soluble ammonia must be converted to free ammonia by adjusting the pH. At temperatures below 40 degrees Celsius, most of the ammonia exists as free ammonia only at pH above 11.5. As a result, ammonia stripping is usually done at higher temperatures, 60 to 80 degrees Celsius, to reduce the demand of chemical for pH adjustment. This model has assumed a temperature of 65 degrees Celsius. The annual chemical costs of caustic for pH adjustment and the capital cost to construct tankage and equipment to house and feed it into the process have also been included in the cost evaluation for ammonia stripping. Ammonia stripping processes are best carried out at atmospheric pressure. Higher pressures increase tower height, which increases capital costs. Stripping factor is basically a safety factor when choosing a design air-to-liquid flow rate. This greatly influences capital costs by changing column height as well as annual costs by impacting air pumping costs. The optimum value is 3.5. Typical stripping processes are able to strip 80 to 95% of the influent ammonia in one pass. The target percent removal of ammonia can be customized and affects tower height and air requirements. This tool assumes that ammonia recovery is done using a single-pass sulfuric acid wet scrubber, which has been designed using the same procedure as the stripping column. The design and cost evaluation have been carried out in accordance with a 15-step procedure laid out in Perry's Handbook of Chemical Engineering and validated by correspondence with Energia. The user can specify the pressure in the stripping column. It is highly desirable to operate ammonia stripping processes at 1 atm. Stripping factor must be in the range of 1 to 5, although a value of 3.5 has widely been reported to yield optimal ammonia recovery. Percent ammonia removal is a treatment target. The model will alter the height of the column and airflow rate based on ammonia liquid to gas mass transfer curves to achieve this removal. The user can choose between carbon steel, stainless steel, or fiber reinforced plastic, FRP. FRP works well for atmospheric pressure and is much cheaper, although for high pressure applications, steel may be needed. The process outputs provided by the tool include design air-to-water ratio based on stripping factor, gas pressure drop, liquid loading rate, packing and tower height, and sodium hydroxide demand for pH adjustment. The model also shows total annual costs, which account for caustic and sulfuric acid costs, in addition to liquid and air pumping costs. The model provides potential yearly revenue from ammonium sulfate sales and a 20-year NPV analysis. Adsorption and ion exchange are absorption processes in which adsorbates are selectively transferred from the liquid phase to surfaces of insoluble, rigid media suspended in a vessel or packed in a column. Ion exchange may selectively remove soluble nitrogen from wastewater. Ion exchange is applicable to agricultural wastewater with relatively low solids, less than 2,000 milligrams per liter, and a wide range of nutrient concentrations. A liquid-solid separation pretreatment step may be required to remove colloidal material which may foul columns. Natural ion exchange media, i.e. zeolites and biochar, saturated with ammonia may be directly land applied to act as a slow-release fertilizer. Design parameters include sizing columns based on empty bed contact time, EBCT, or days to breakthrough, defining the resin characteristics or selecting from a list of reference resins, specifying delivery distance, pumping efficiency, and backwash requirements. The user may size columns based on an empty bed contact time or time to breakthrough. EBCT is the measure of time during which water is in contact with the resin in the ion exchange vessel. Time to breakthrough is the predetermined time for the resin to become saturated with ammonia and require replacement, e.g. every 30 days. The user may input known ion exchange resin characteristics, yes, or select a reference adsorbent from the drop-down list, no. The reference adsorbents list is based on values from references for bulk density, resin diameter, resin cost, ion exchange Langmuir isotherm parameters. The model-generated outputs include resin usage, number and diameter of columns, pumping flow rate to maintain minimum hydraulic loading rate or EBCT, energy demand, greenhouse gas emissions from ion exchange resin production, O&M and staffing requirements, total annual costs including equipment rehabilitation and replacement, resin, energy, and labor, potential fertilizer revenue generated from land applied ammonia saturated resin, capital cost, and 20-year net present value.